The night sky isn't what it seems. You look up and you see stars, you see galaxies, just scattered. But that emptiness, it's an illusion. There's a structure underneath. A hidden architecture, a cosmic web. These invisible threads, they've been organizing everything, dictating where galaxies go for billions of years. So there's this secret blueprint, and it controls every galaxy. How do you find something like that? How was it discovered? The science behind it, it's mind-bending. And then what does it mean for our place in all of this? By the end, you won't see a random scatter. You'll see a map, a meticulously organized map. Galaxies gather in specific places. They clump in clusters along filaments. But why there? What force first drew that map? An invisible skeleton shaping everything we can see. And what that means for us? That view of islands in a dark sea was a beautiful mistake. For a long time, astronomers looked at the sky and saw each galaxy as its own world, a lonely beacon in a silent, black ocean. That was the model based on what the telescopes could show, and it made sense because the distances were so vast, the spaces so dark, that emptiness seemed like the only answer. But science has a way of showing that our intuitive answers are often wrong. The truth didn't come from looking at the bright spots. It came from questioning the darkness. What if the spaces between galaxies weren't empty? What if that void was hiding the universe's real structure? That was the shift. We stopped seeing galaxies as isolated islands. We started looking for the bridges, and we realized the dark sea wasn't a sea. It was a spiderweb, a colossal, three-dimensional web on a scale that's hard to even grasp. The bright galaxies we see are just the knots, the intersections where this web pulls matter together. The filaments of the web are made of something we can't see directly. Dark matter, it forms an invisible skeleton with a thin haze of primordial gas. This is the cosmic web. It means every galaxy, every cluster, is in a specific place for a reason. They're not drifting randomly, they're hanging, suspended along this grand architecture. The old idea of island universes wasn't just updated, it was overturned. The universe's largest structure isn't a featureless expanse. It's an organized, dynamic network, and that leads to a new question. If this web is real, how did we ever find it? The evidence was just sitting there. For a long time, telescopes could only show us a flat view of the sky, just points of light on a dark background. It was like looking at a single slice of a cake. You could see the sprinkles, but you couldn't tell how deep it was or how the layers fit together. The change happened when they figured out how to measure not just where a galaxy is, but how far. They used redshift. When a galaxy moves away, its light stretches, shifting toward red. The faster it moves, the bigger the shift. And since the universe is expanding, a galaxy farther away is moving faster. So by measuring the redshift, you get the distance. Now you could plot points in real three-dimensional space. In the 80s, the CF a redshift survey started doing that. They plotted thousands of galaxies. Everyone thought it would look like a uniform fog, a smooth spread of matter, but it wasn't like that at all. The galaxies weren't random. They formed this huge, complex pattern. On the new 3D maps, they clustered into giant walls and long, thin filaments, like threads, and these structures surrounded huge, empty spheres. Voids, some of them hundreds of millions of light years across. The whole thing looked less like fog and more like a sponge, or maybe a network of neurons. This was the first real look at large-scale structure, the shadow of a cosmic web drawn in starlight. The galaxies weren't the structure, they were just the bright markers. Beads on invisible strings, the pattern was so big, so organized, it couldn't be random. It was a fingerprint, a blueprint from the very beginning. That map needed an architect. For a blueprint that big, you need a material that can shape the whole universe without ever being seen. The main force drawing the cosmic web is gravity. But gravity needs mass, and most of the mass in the universe isn't in the stars or the gas we can see. It's in something else, something called dark matter. This stuff makes up about 27% of everything. We know it's there because of its gravitational pull. We see it in how galaxies spin, how light bends around clusters. But it doesn't emit light, it doesn't absorb it, it doesn't interact with light at all. It's invisible to our normal telescopes. It only talks through one language, gravity. So how does an invisible substance draw a visible map? It starts in the first fractions of a second after the universe began. Even then, in that hot, dense state, it wasn't perfectly smooth. Because of quantum mechanics, there were tiny, random ripples, minute differences in density from one spot to the next, like a perfectly still pond, but at a microscopic level, it's never truly flat. There are always tiny vibrations. Then the universe went through inflation, a period of rapid expansion that stretched those tiny quantum ripples across the entire cosmos. Those microscopic vibrations became the seeds for the largest structures. They were imprinted onto the dark matter as slight overdensities, places where there was just a little bit more of this invisible stuff. For billions of years, gravity did its work. It's a patient sculptor. Regions with slightly more dark matter had slightly stronger gravity. They pulled in more dark matter from around them. Over eons, this process snowballed. The denser patches grew, drawing matter into vast sheets and long rivers. The less dense regions emptied out, becoming the great cosmic voids. What formed was an intricate, three-dimensional network, a web. You can think of dark matter as the invisible framework, the steel girders of a skyscraper. It defines the shape, the skeleton of the structure. The ordinary matter, the gas that forms stars and galaxies, that's just the glass and concrete. It follows the shape the dark matter skeleton has already built. It flows along the filaments and pools at the intersections, lighting up the knots of the web. So the cosmic web we see traced in galaxies is first a dark matter web. It's a gravitational blueprint drawn in invisible ink. The glittering paint of stars and galaxies is applied later. Every cluster you see, every filament of galaxies, exists because an unseen architecture of dark matter dictated it should be there. That changes the story. We're not just looking at where galaxies are. We're looking at the fossilized imprint of the universe's first moments, magnified to a cosmic scale by the steady, persistent pull of gravity. The maps started showing specific landmarks. These huge structures gave the invisible web a geography we could actually name. One of the first was the Great Wall, sometimes called the CF, Great Wall. It wasn't a wall in the normal sense. It was an immense, flattened concentration of galaxies. It stretched for hundreds of millions of light years. To give a sense of scale, if our Milky Way were a single grain of sand, this wall would be wider than the entire continent of North America. A sheet of galaxies so vast it challenged our ideas about how matter should be spread out. It was a filament of the web seen edge-on, a thread in the grand tapestry. But the presence of such huge structures meant there had to be an equally huge absence. The maps showed the voids. These are regions of space, hundreds of millions of light years across, that have almost no bright galaxies. One of the most famous is the Boötes void, a spherical region so empty that if our Milky Way were at its center, we wouldn't have found other galaxies until the 1960s. A cosmic desert on a scale that's hard to grasp. These voids aren't accidents, they're essential features, the negative space that defines the web's positive structure. Think of it like a sponge. The solid material of the sponge is the web of dark matter and galaxies. The holes are the voids. You can't have one without the other. Gravity pulled matter into the filaments and sheets, and in doing that, it drained matter from the regions in between. The voids are the inevitable result of the universe organizing itself. This pattern of great walls and vast voids matches exactly what the dark matter model predicts. It shows the cosmic web organizing by a simple, powerful rule. Matter flows toward the densest parts of the gravitational skeleton. Where the dark matter filaments are thickest, galaxies form most prolifically, especially where filaments cross. These intersections become the great clusters, the bustling cities of the cosmos, and the regions that were initially slightly emptier get emptier still, becoming the silent voids. So the web's power is shown in both presence and absence. The glittering walls and the dark voids are two sides of the same coin, both dictated by the same underlying blueprint. That means the emptiness between galaxies isn't a failure or a mystery. It's a signature. It's the fingerprint of the web's architecture, a silent testament to the organizational force that's been sculpting the universe from the start. And if both the bright clusters and the dark voids are part of the plan, then what happens in the places where the web's threads are pulled the tightest? The dark matter skeleton is the framework, the blueprint, but a blueprint isn't a building. To light up, the universe needed the stuff we can see, ordinary matter. Protons, neutrons, electrons, that's the cosmic paint, and it had to follow the lines already drawn by the dark matter. After the Big Bang, the universe was this hot, smooth soup. Primordial gas, hydrogen and helium mostly, but it wasn't perfectly smooth. The dark matter web had already started forming its gravitational valleys and mountains. And gravity pulls on everything, dark matter, ordinary matter, all of it, so that primordial gas began to flow. It streamed out of the empty regions, the voids. It poured into the gravitational valleys the dark matter carved. It rushed along the filaments, these cosmic superhighways stretching across everything. It's like water on a landscape after heavy rain. The water doesn't fall randomly. It follows the land's contours. It gathers in the gullies, flows into the streams, pools in the lakes at the lowest points. The dark matter web is that landscape. The ordinary gas is the water, and where the filaments cross, the nodes, those are the deepest lakes. As this river of gas flowed, things started happening. The gas particles bumped into each other. They radiated heat away, they slowed down, and as they slowed, they began to clump. Density increased. In the densest parts of the filaments, especially at the busy intersections, vast clouds of gas began to collapse under their own gravity. Inside these collapsing clouds, pockets got so dense, so hot, that nuclear fusion ignited. The first stars were born, and where many stars gathered, bound by gravity, the first galaxies flickered into existence. So the web doesn't just tell galaxies where to be, it tells them how to live. The most active, the most massive, the brightest galaxies are almost always at these intersections. They're the megalopolises, fed by a constant influx of fresh gas flowing in from multiple filamentary highways. A galaxy out on a lonely filament, far from a major intersection, is like a small town on a single road. It gets less traffic, less material, it grows more slowly, it might stay a quiet, modest spiral. The cosmic web is more than a map, it's a delivery system. A vast, slow-motion irrigation network. It channels the raw material for building stars and planets to very specific cosmic addresses. It determines not just a galaxy's location, but its destiny. Its size, its activity, the story of the stars that will shine inside it, the glittering cities and the quiet towns of the universe, they're all products of this ancient, invisible flow. We know the story is true because we didn't just look at the sky. We built new universes inside supercomputers. That's the third discovery. It happened in silicon. Cosmologists create digital universes. They start with a virtual box of space filled with particles for dark matter and gas, all following the known laws of physics. They set the initial conditions to match what we think existed just after the Big Bang, including those tiny quantum ripples. Then they press play. The simulation runs, calculating the gravitational pull between trillions of particles over billions of virtual years. It's a cosmic fast-forward button. Projects like the Millennium Simulation and IllustrisTNG have done this, and the results are breathtaking. As you watch, you don't see a smooth, boring fog. You see structure emerge. Filaments of dark matter slowly pull themselves together, stretching across the growing voids like threads of a spiderweb. At the intersections, dark matter halos merge and grow, becoming the gravitational anchors for galaxies. The ordinary gas follows, flowing along those digital highways, cooling, collapsing, forming stars right on schedule. The final snapshot, after 13.8 billion virtual years, is a map. And when you compare that digital map to the real maps from our galaxy surveys, the match is uncanny. The same great walls, the same vast voids, the same sponge-like structure. The simulated universe, built only from our equations for gravity and dark matter, weaves the exact same cosmic web we observe. That's a profound validation. It means the ingredients we've identified, those initial ripples, dark matter's gravity, the flow of gas, they're not just a good guess, they are sufficient. They are the recipe. The computer becomes a laboratory, a time machine. It lets us run the experiment of cosmic evolution over and over. We can tweak the ingredients. What if dark matter behaved differently? What if there was more ordinary matter? Every change produces a different cosmic web, and by finding which simulation matches our reality, we zero in on the truth. So the web is no longer just an observed pattern or a theoretical idea. It is a predicted outcome confirmed in a digital universe. The simulation proves the blueprint works. It shows the hidden architecture we infer from starlight isn't a coincidence. It's a direct, inevitable consequence of the laws that have shaped everything from the first instant to now. A skeleton needs more than bones to work. You have the dark matter filaments, the framework, the gravitational pathways, but that's not what builds stars. That's something else, something far more diffuse, a ghostly plasma that fills the spaces between galaxies, the intergalactic medium. It's like the bloodstream of the cosmic web. And it's the largest reservoir of ordinary matter in the universe. This isn't the cold, dense gas inside a galaxy. It's incredibly thin, a wispy haze of hydrogen and helium, atoms stripped of their electrons, superheated to millions of degrees. So diffuse that in a space the size of a room, you might find just one atom, but stretched across those colossal filaments, it adds up, more than all the stars and galaxies combined. And it's always moving, following the pull of the dark matter skeleton. This hot gas flows. It streams out of the great voids, channeled into the filaments, rushing toward the intersections where galaxies cluster. It's a constant, slow-motion river of raw material. So a galaxy at a major node is like a city at the confluence of rivers. It's continually fed. Fresh gas flows in along these filamentary highways, fuel for new generations of stars. That's how the web sustains itself. It's not a static sculpture, it's a dynamic circulatory system. But how do you see a river of gas that's almost perfectly transparent? You look for its shadow. The key is a cosmic lighthouse, a quasar, the brilliant cores of distant galaxies, shining with the intensity of 1 trillion stars. Their light travels for billions of years to reach us, and on that journey, it passes through the filaments of the cosmic web. The atoms in that medium, sparse as they are, can absorb very specific wavelengths of that light. When astronomers split the quasar's light into a spectrum, they see dark lines, missing colors. Each line is a fingerprint, a sign that the light passed through a cloud of hydrogen or helium at a specific density, a specific temperature. By studying thousands of quasars, by looking at the patterns of these absorption lines, scientists can map the gas. They can trace its distribution, measure its temperature, chart its flow. It's an indirect vision, but a powerful one. These spectral fingerprints reveal the hidden rivers. They prove the filaments aren't empty. They're brimming with this hot, flowing plasma. And that changes our view of a galaxy's life. A galaxy isn't a closed system. It isn't born with a fixed amount of gas to slowly use up. It's an open node connected to a vast network. It can receive new supplies from the web, and it can also expel material back into it through stellar winds, supernova explosions. The intergalactic medium is the connective tissue. It means the galaxy next door, millions of light years away, isn't truly separate. We're all bathed in the same cosmic currents, linked by an invisible flow of matter that's been cycling since the first stars were born. The universe isn't a collection of isolated islands. It's a single, breathing organism with a web for a nervous system and rivers of plasma for blood. The proof is in the missing colors, in the light that isn't there. Astronomers look at the universe's brightest beacons to see the dark rivers, quasars. Their light is so intense it can travel for 12 billion years and still reach us, but on that journey it doesn't travel through nothing, it cuts through filaments, through diffuse gas, and that encounter leaves a mark, a signature. They call it the Lyman-Alpha forest. Here's how it works. The gas between galaxies is mostly hydrogen. And when a hydrogen atom is in its lowest state, it absorbs a very specific wavelength of ultraviolet light. That wavelength is the Lyman-Alpha line. Now take a single beam of light from a distant quasar. As it comes toward us, it passes through cloud after cloud of this hydrogen. Each cloud is at a different distance. And because the universe is expanding, each one is moving away from us at a different speed. That motion stretches the light. It shifts the absorption. So every cloud absorbs the quasar's light at a slightly different wavelength. What you get isn't one dark line in the spectrum, it's hundreds, thousands. A whole thicket of absorption lines, each one is a record. A specific hydrogen cloud the light passed through. That's the forest. By analyzing this forest, scientists can do something. They can reconstruct a map, a one-dimensional map. It's like a core sample of the universe along that single line of sight. Every line tells them the density, the temperature, the location of the gas that created it. Then they point telescopes at many quasars in different directions. They get many core samples. And they can stitch these together to build up a three-dimensional picture, a picture of how the gas is distributed, and that picture shows the filaments. It reveals the web's architecture, not in starlight but in the shadows cast by the gaseous threads. The Lyman-Alpha forest is more than a trick. It's a direct window, a window into the cosmic web's plumbing. It shows us the vast spaces between galaxies aren't empty. They're structured, they're organized. Filled with this tenuous, flowing material, it confirms the dark matter skeleton has a gaseous counterpart, exactly what the simulations predicted. Every absorption line in that forest is a whisper. A whisper from a strand of the web. It's a testament to an architecture so vast, so fine, that you can only see it by the light it takes away. The most powerful parts of the cosmic web are its great cities. Where thick filaments cross, gravity has built something monumental, a galaxy cluster. These aren't just groups of galaxies. They're the most massive structures in the universe, bound by gravity. Think of a galaxy like our own. Then imagine hundreds, even thousands of them, all swarming together in a space tens of millions of light years across. That's a cluster, but the galaxies are just the visible part. For every bit of starlight, there's far more we can't see. The space between the galaxies is filled with a superheated plasma, a gas so hot it glows in X-rays. This gas often weighs more than all the stars in all the galaxies put together. and holding this entire metropolis together is a huge, invisible halo of dark matter. The dark matter skeleton of the Webb is thickest right here at these intersections. Its gravity is the foundation, the thing that keeps everything from flying apart. Clusters like our nearby Virgo cluster or the distant Coma cluster, they're not accidents. They're the inevitable destinations. For billions of years, the cosmic web has been channeling matter toward these hubs. Smaller groups of galaxies traveling along the filaments merge together. Rivers of intergalactic gas flow inward, and they compress and heat up as they fall into the cluster's deep gravitational well. A cluster is a cosmic terminus, a place where the web's threads are gathered and tied into one colossal knot. Studying these metropolises gives us a magnified view of the web's power. The hot gas acts like a tracer, outlining the shape of the cluster's gravity well. By measuring its temperature and how it's spread out, we can weigh the whole cluster. And that weight tells us about the dark matter that dominates it. Clusters become natural laboratories. Their signposts, their existence, their number, how they're distributed across the universe, it all serves as a test. It confirms the predictions of our models about how the cosmic web formed and evolved. When we map the local universe, these dense, brilliant clusters are the brightest beacons. They mark the major intersections of the grand design. They show us where the web's pull was strongest, where the universe chose to build its greatest gatherings of matter. But if clusters are the web's bustling cities, what's at the other extreme? In the vast tracts of space the web deliberately left empty. The great voids are the silent counterpoints to the web. Clusters roar with energy, but voids are the cosmic deserts. They're these huge expanses, so empty they can stretch for hundreds of millions of light years. Maybe just a handful of dim, lonely galaxies inside them, and these aren't accidents. They're the logical outcome of how the web organized. Gravity pulled matter into the filaments and nodes, and in doing that, it drained the regions in between. A void is what's left behind, a place the web deliberately bypassed, so studying these empty spaces is just as important as studying the crowded clusters. They define the shape of the web as much as the threads do. The Boötes void, for instance, is a spherical region about 330 million light-years across. If our Milky Way were at its center, the night sky would be almost devoid of other galaxies. It would be a profoundly different view. These voids are the ultimate testament to the web's power, its ability to create not just structure, but also the absence of structure on the grandest scales. They're the negative space that makes the positive design visible. But then, how do we see the threads of the web themselves, especially the hot gas flowing within them? The light from galaxies shows us the knots, but the filaments are often too faint, too diffuse for our telescopes to capture directly. We needed a new way to look. A method that didn't rely on the web's own light, but on how it changed light passing through it, and that method exists. It's called the Sunyaev-Zel'dovich effect. It uses the oldest light in the universe as a cosmic backlight. That light is the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of space. It's a nearly uniform glow, a snapshot of the infant universe. But as this ancient light travels for billions of years to reach us, its journey isn't unimpeded. When it passes through a massive galaxy cluster, it encounters the superhot electron gas that fills the space between the cluster's galaxies. These high-energy electrons collide with the SIMB photons, giving them a tiny but measurable boost in energy. It's like the light is passing through a fog of energetic particles and getting a slight kick. This interaction leaves a distinct shadow, a cold spot, in the map of the cosmic microwave background at the cluster's location. It's not that the cluster is emitting cold light, it's that it has subtly altered the light coming from behind it. So this effect is a revolutionary tool. Telescopes like the Planck satellite and the Atacama Cosmology telescope scan the sky, not for visible starlight, but for these specific distortions in the CMB. By finding these shadows, they can locate galaxy clusters, even ones that are extremely distant and faint. They've catalogued thousands this way, but the power of the Sunyaev-Zel'dovich effect goes even further. It's sensitive enough that scientists are now beginning to use it to detect the hotter, fainter gas within the filaments of the cosmic web itself. The rivers of plasma flowing between the clusters also interact with the CMB light, creating a far subtler imprint. By carefully stacking and analyzing data, astronomers are starting to trace this filamentary glow. This turns the entire cosmic microwave background into a giant screen. And the cosmic web, with its clusters and filaments, becomes a silhouette projected onto it. We're seeing the universe's largest structure not by the light it emits, but by the shadow it casts on the first light of creation. It's a profound confirmation the architecture we predicted is really there, etched into the afterglow of the beginning. That ancient light carries a timeline. What we see now is just one frame, a snapshot. The cosmic web today wasn't always this defined. It grew, it evolved, it has a history. In the early universe, a few 100 million years after the Big Bang, the web was faint. A ghostly sketch. The density contrast from those quantum ripples were incredibly slight. The dark matter skeleton was there, but the filaments were smoother. More diffuse, the voids were smaller. The whole structure was like a faint watermark on space, waiting for gravity to bring it into focus, and then gravity went to work. It's a slow process, relentless, called hierarchical structure formation. Small things merged to form bigger things. Small clumps of dark matter attracted more dark matter. They grew into halos, and these halos, guided by the filament network, drifted together along the threads. They collided, they merged, building larger and larger structures. You can think of it like a river system on Earth. First, tiny trickles form in the soil. They merge into streams. Streams flow into creeks, then rivers, and finally into something like the Amazon. The cosmic web followed a similar logic, but in 3 dimensions, over billions of years. As this happened, the web's features sharpened, filaments thickened. They became the clear superhighways we see in simulations. The voids expanded dramatically. Matter was pulled out of them and into the surrounding filaments. They became the great cosmic deserts. Matter drained from the lower density regions, feeding the growth of the nodes, the galaxy clusters. The web became more pronounced, more complex, more intricate with time. The universe's large-scale structure didn't spring into being fully formed. It assembled itself, piece by gravitational piece. We can see this growth directly by looking back in time. When astronomers point their most powerful telescopes at extremely distant galaxies, they're seeing light that left when the universe was young. By mapping these ancient galaxies, they can reconstruct the cosmic web as it existed billions of years ago. And what they see matches the story. The web back then was more delicate. The filaments were thinner, the clusters were smaller and less numerous, the voids were not as vast. It's a younger, less organized version of the grand design we see today. This historical perspective changes everything. The cosmic web is not a frozen sculpture. It's a dynamic, evolving entity, continuously at work even now. Reshaping the distribution of galaxies across cosmic time. Galaxies are still flowing along the filaments. Clusters are still growing, cannibalizing smaller groups that fall into them. The web is alive with slow, gravitational motion. It means the map of the universe is not fixed. It's a page in an ongoing story, one where gravity is the author. And every galaxy is a character following the paths laid down at the dawn of time. For a long time, the cosmic web was just an idea. We had evidence, but it was scattered. A survey in one place, a simulation in another. You could plot a few thousand galaxies, see a pattern, but it wasn't the whole thing. It was like looking at a few towns and trying to picture a continent. We needed the whole picture, a complete survey, something that could turn the theory into something you could see. That happened with the Sloan Digital Sky Survey. It was one telescope with one job: to photograph the sky night after night for years to make a digital map, but it did more than take pictures. It used spectroscopy. It took the light from millions of objects, galaxies, quasars, and split it into colors. It measured the redshift for each one. It found the distance, so those flat pictures became a three-dimensional atlas. The scale was something new. Sloan mapped over a third of the sky. It found the positions and distances for more than 3 million galaxies, and with that, scientists could build a map. A map of the local universe that was both wide and deep. It's one of the most important images we have, the SDSS galaxy map, the cosmic web map. You look at it and the theory is gone. You just see it, this vast network, like a brain or the structure of a sponge, delicate filaments of galaxies stretching out. They curl around these huge spherical voids, empty spaces. Great walls of galaxies, like the Sloan Great Wall, curving for millions of light years. This wasn't a simulation. This was the real universe plotted point by point. The map gave you something numbers couldn't, a concrete visualization. It turned the model into an observed fact. Now scientists could measure it. How thick are the filaments on average? How are the galaxies distributed along them? How do the void sizes relate to the density around them? Sloan had the data for those answers. It became the standard reference, the benchmark for testing every theory and simulation. This detailed portrait did more than confirm the web. It showed its texture. The web isn't perfectly uniform. Some filaments are thick, rich with galaxies like superhighways. Others are faint, just tenuous threads. Some voids are almost perfectly empty. Others have a few isolated galaxies, void galaxies. The Sloan map captured the large-scale structure, all its messy, beautiful complexity. It showed that the cosmic web isn't just a skeleton. It's the living anatomy of the cosmos, with all its variations laid bare. This dataset didn't just fill in blanks. It defined the canvas we now use to chart the history of everything. Our most basic measurement of the cosmos could be a little off, and it might be because of where we are. That's the Hubble tension. It's a quiet problem in cosmology. We have two main ways to figure out how fast the universe is growing. One way looks at the very early universe, at that ancient light, the cosmic microwave background. That gives us a precise rate from 13.8 billion years ago. The other method looks locally, at nearby supernova and bright objects. These two methods should match. They're measuring the same universe, but they don't. The local measurements keep showing the universe expanding a bit faster than the early data says it should. It's a small difference, but it's stubborn, like two perfect clocks ticking at slightly different speeds. This isn't a mistake, it's a tension, a clue that our model is missing something. And one idea brings us back to the cosmic web. We aren't in a perfectly average part of space, we're inside a structure. Our Milky Way is part of the local group. And that's on the edge of the Virgo cluster. And that cluster is just a small piece of a much bigger supercluster called Laniakea. Laniakea is a huge overdensity in the cosmic web. A gravitational watershed hundreds of millions of light years across. We are inside it, and that matters. The gravitational pull of a structure that massive can give our whole local region a slight drift, a motion relative to the overall expansion. It's like being in a gentle current within a larger river. If you measure the river's flow only from your boat, your measurement might be off by the speed of the current you're riding. So if our galactic neighborhood is being tugged by the gravity of Laniakea, then our local measurements of the expansion could be biased. We might be mistaking some of our own motion for a faster universal expansion. The cosmic web isn't just a backdrop. It's an active participant. Its local geometry and gravity could be imprinting itself on our most important numbers. This reframes everything. We aren't passive, detached observers looking at a distant stage. We are embedded in the very architecture we're trying to measure. Our address in the cosmic web might subtly color our view of everything. Solving the Hubble tension might not need new physics. It might just need a better map. A precise accounting of how the local threads of the web are pulling on us. It's a reminder that to see the universe clearly, we have to understand our own place within it. The web starts at the very beginning, in that first instant, before stars, before atoms, before matter and energy were even separate things. And in that instant, the universe went through something called inflation. Space expanded faster than light. It went from something smaller than an atom to something huge almost instantly, and during that stretch something got locked in. The universe is fuzzy at the quantum level. There are tiny random fluctuations, and inflation took those tiny quantum ripples and blew them up to a cosmic scale. A spot that was a little denser became a huge dense region. A spot that was a little emptier became the seed for a void. That was the imprint, the initial conditions. The gravitational blueprint for everything was drawn right then, but that blueprint was invisible for a long time. For about 380,000 years, the universe was a hot, opaque fog. Light couldn't get through, it was just scattering. Then, as it cooled, recombination happened. Protons and electrons came together to make neutral hydrogen. The fog cleared, the universe became transparent, and that first light, which had been trapped, finally streamed out. We see that light today. It's been cooled and stretched by 13.8 billion years of expansion. We call it the cosmic microwave background. It's the oldest picture, a snapshot of the infant universe, and in that snapshot you see the seeds. The CMB isn't perfectly smooth. When we map it with satellites like WMAP and Planck, you see a pattern, tiny variations in temperature, warmer spots and cooler spots. The differences are incredibly small. 1 part in 100,000, but that's everything. Each warmer spot was a slightly denser region back then. Each cooler spot was a bit emptier. These anisotropies are the direct imprint of those quantum fluctuations. They're the fossilized ripples from the beginning, stretched across the sky by inflation. This map is like a Rosetta Stone. By analyzing the patterns in these temperature variations, the size of the spots, how they correlate, cosmologists can run the clock forward. Using the laws of physics, mainly gravity, they can simulate how those slight overdensities attract more matter, how they grow and merge over billions of years. The predictions from the CMB are incredibly precise. They tell us what large-scale structure should form, the distribution of filaments, clusters, and voids. The scale of the cosmic web. Then we look at the real universe with surveys like Sloan. We map the actual galaxies and clusters, and the agreement is breathtaking. The pattern in the afterglow of the Big Bang perfectly predicts the sponge-like structure we see today. The cosmic microwave background is the founding document. The cosmic web is the civilization that grew from it. This match ties the very large to the very small, the present to the first moment. We're reading the universe's opening chapter and seeing how the plot unfolds. Every story ends, the cosmic web will end too. The force that built it will tear it apart. For billions of years, gravity was the architect. It pulled matter together into filaments and clusters, but now another force is in charge, a more mysterious force, dark energy. It's not a substance like dark matter. It's a property of space, a kind of repulsive gravity. It makes the universe expand faster, and as it gets stronger, it changes the rules. Right now, dark energy and gravity are in a tug of war. On the scale of galaxy clusters, gravity still holds sway. It binds the Virgo cluster. It channels gas along the superhighways, but dark energy works on the largest scales. It pushes the fabric of space apart, and it's winning. The acceleration is real. We can measure it. Every day, the space between clusters grows a little faster. So the fate of the web is written in the laws of physics. Over tens of billions of years, dark energy's influence becomes absolute. The grand architecture we see will slowly dissolve. It will be gradual, relentless. First, the most distant threads go. The delicate filaments connecting superclusters will stretch and thin. The rivers of gas flowing along them will slow to a trickle. Then stop, cut off. Galaxies on the outskirts will drift, their supply lines severed. Next, the local web unravels, the structure binding our Laniakea supercluster. The gravitational pull defining these watersheds will be overcome by the accelerating expansion of space. Bustling intersections become isolated archipelagos. Galaxy clusters stop merging, they become lonely islands in a sea of growing darkness. The final stage is a quiet solitude, each galaxy cluster, then each galaxy group marooned. In its own pocket of space, with no fresh gas flowing in, star formation ceases. Existing stars burn out, one by one. The universe, once vibrant with structure, grows cold. Dark, incredibly diffuse, the sponge-like structure, the great walls and voids smoothed away by the relentless stretching of space. The cosmic web isn't permanent. It's a phase, a magnificent but temporary chapter, sandwiched between a hot, dense beginning and a cold, empty future, dictated by dark energy's silent push. This gives our time a special significance. We live in a cosmic springtime, a golden age. The web is at its most intricate. We can still see the threads. Trace the flows, witness galaxies being fed. In a future so distant, observers would look out and see only emptiness, no evidence of the vast tapestry. Our ability to map the web today is a privilege of timing, a glimpse of the universe's structure during its brief, brilliant prime. The largest structure in the universe is invisible. We see the galaxies, the bright spots, but the real framework, the skeleton, is dark matter. It doesn't show up in our telescopes. To find it, you have to watch how it bends light. That's gravitational lensing. It comes from Einstein's theory. Massive things warp spacetime like a bowling ball on a rubber sheet. The sheet curves. Roll a marble past and its path bends. Light does that. When light from a faraway galaxy travels and it passes near a big mass of dark matter, a filament or a cluster, its path gets curved. The image of that galaxy gets stretched, magnified, distorted, sometimes into faint arcs, sometimes into multiple images. It's a funhouse mirror made by gravity. But the distortions we need to see are very subtle. These dark matter filaments are massive but spread out. They don't make perfect rings. Instead, they cause a slight, coherent warping. In the shapes of thousands of background galaxies, any single galaxy's shape is random. But if you see thousands of them, all stretched slightly in the same direction, you know something massive is in front, bending the light. It's like looking through wavy glass. So astronomers measure these tiny, systematic distortions across huge areas of sky. And they work backward. They calculate the mass that must be there to cause that bending. They can draw a map of where the invisible mass is. Projects like the Dark Energy Survey do this. They take deep images of millions of galaxies. Software analyzes the shapes, looks for that weak lensing signal. The result is a map, not of light but of pure mass. A map of the dark matter web, the first real charts of the hidden architecture, and the confirmation is something. These dark matter maps line up perfectly with galaxy maps. From surveys like Sloan, the peaks in the dark matter are exactly where the great galaxy clusters sit. The faint, sprawling ridges trace the same filamentary paths the luminous galaxies follow. Light follows mass. The bright beacons are just tracing the contours of an unseen landscape. This is the closest we've come to seeing dark matter directly. We're not detecting the particles, we're seeing their gravitational influence on the fabric of reality. It proves the cosmic web is first a dark matter structure. The luminous universe we see is decorative, painted onto a framework we can't see. Every arc of light, every stretched galaxy shape, it's a message written in the warped paths of light, saying the empty spaces are full and the darkness has shape. For decades, astronomers did a kind of inventory. They counted up all the ordinary matter they could see. The stars, the gas inside galaxies, everything made of atoms, and the total came up short. It was far less than it should have been, because we have a very precise recipe for the early universe from the cosmic microwave background. And according to that, about half of all the ordinary matter from the Big Bang was just gone, unaccounted for. That was the missing baryon problem, a huge discrepancy. If the numbers from the beginning were right, that matter had to be somewhere. But where do you hide half the atoms in the cosmos? The answer was in the emptiest places. In the vast stretches between galaxies, the cosmic web, it wasn't just a map of dark matter, it was also a reservoir. The missing atoms were there the whole time, spread out in an extremely hot, incredibly thin gas that fills the filaments. They call it the warm-hot intergalactic medium, the WIM. This gas is heated to temperatures between 100,000 and 10 million degrees. At those temperatures, it doesn't glow in visible light. It's almost perfectly transparent, and it's so diffuse, in a cubic meter of space you might find just one atom. But the volume is immense. Those colossal threads stretch across billions of light years. And when you add it all up, it accounts for everything. This faint, searing plasma is where most of the universe's normal matter has been. Finding something that hot and that invisible required a new way of looking. You have to look in the specific wavelengths it does interact with, ultraviolet and X-ray light. The problem is, any single filament is far too faint to see directly. The signal is drowned out. So astronomers use a technique called stacking. They take precise maps of the cosmic web from galaxy surveys. They identify the locations of thousands of filaments. Then they take X-ray and ultraviolet observations of those same areas of sky, and they stack them. Layer all the data on top of each other, aligning the predicted filament locations. It's like combining thousands of faint, underexposed photographs. The noise averages out, and the faint, collective glow of the WIM emerges, and it works. In recent years, observatories like the Newton Space Telescope have used this method. They've detected the signatures of highly ionized oxygen and other elements in the web's filaments. They are seeing the hot gas. The missing baryons have been found. They were never lost. They were just woven into the fabric of the universe itself, flowing along the grand avenues of the cosmic web. This closes a major chapter. It confirms that the luminous galaxies are just the bright knots in a much larger tapestry. Most of the ordinary matter, the stuff we are made of, exists in a form we can barely perceive. A whispering, million-degree haze that traces the invisible architecture of everything. The James Webb Space Telescope works like a time machine. It sees infrared light that's been stretched out over billions of years as the universe expanded. So we're looking back at the very first galaxies. We're seeing the frontier, the time when the cosmic web was just starting to form, and what it looks like is a construction site. A brilliant, chaotic construction site from when the universe was young. We're not seeing a finished, intricate web yet. We're seeing the earliest threads. Galaxies that aren't isolated but already linked in these faint, sprawling chains. These are the primordial filaments. The universe was less than 1 billion years old then. They're thinner, more fragile than the grand structures we see today, but the blueprint is there. The dark matter skeleton was already in place, and the first galaxies were lighting up along its lines. Webb's infrared vision cuts through the cosmic dust too, dust that hid these early events from other telescopes. It shows us the raw process. We can see rivers of cold gas, the fuel for stars flowing along those dark matter highways, funneling into the growing galactic hubs. The telescope is catching galaxies in the act of being fed by the Webb. Their furious star formation is directly powered by this ancient, organized delivery of material. And then there's the timeline. How quickly did gravity pull those first strands together? When did the first major nodes, the great clusters in the making, start to shine? Webb's data suggests it happened fast. The Webb's architecture emerged rapidly. Galaxies ignited at its intersections far earlier than a lot of models predicted. But Webb is showing a new layer of complexity. These first galaxies weren't passive. They were dynamic, violent. Their massive stars and growing black holes blasted out enormous energy, heating the surrounding gas, pushing it around. This feedback began to alter the very filaments that fed them. It could slow down further star formation or clear out pockets of the Webb. We're watching the first conversation between galaxies and the cosmic web that birthed them, a dialogue of creation and disruption, one that would shape the universe for eons to come. So with every deep field image, Webb isn't just giving us baby pictures of galaxies. It's a front row seat to the moment the universe's grand design first flickered into view. The blueprint builds galaxies, but then it gets rewritten by them. For a long time, the story was simple. Gravity pulls gas in from the cosmic web, galaxies form. But that's missing something, a violent chapter. Galaxies aren't just passive, they talk back. They push against the structure that made them. That conversation is called feedback. And it's one of the most powerful forces in a galaxy's life. It starts with the first stars, the massive ones. They live fast and die young. Their deaths are supernova. These explosions release more energy in seconds than our sun will in its whole life. That energy floods out. It heats the surrounding gas to millions of degrees. It drives shock waves. Those shock waves can sweep up gas and fling it out of the galaxy. They can compress other clouds and trigger new stars. Or they can heat the gas so much it can't collapse to form stars at all. A galaxy's starlight is gentle, but the collective fury of its supernova is a hurricane that reshapes its local part of the web. Then there's the central engine. At the heart of almost every large galaxy, a supermassive black hole. When gas falls onto it, it forms a swirling, superheated disk. And from the poles, the black hole can fire out jets. Jets of particles and radiation moving near light speed. They can be millions of light years long. They punch through the galaxy and out into the space between galaxies. Where they strike, they deposit colossal energy. They heat the gas around them. That prevents it from cooling and falling back in to form new stars. In the most extreme cases, they blow huge, empty bubbles in the hot gas of a galaxy cluster. This is feedback on a cosmic scale. The black hole acts as a regulator, a thermostat. It stops the galaxy from growing too big, too fast, so the relationship flips. The Webb's filaments deliver cold gas. That's the fuel for stars and black holes. That activity ignites. The explosions and jets heat the gas, they push it around. They enrich it with heavy elements from stellar furnaces. This processed, energetic gas gets recycled. It flows back into the Webb's filaments, and that changes their temperature. Their chemistry, their future ability to form new galaxies. It's a dynamic loop, a constant exchange. The Webb builds the galaxies, and the galaxies maintain the Webb. They stop it from collapsing all its gas into stars too quickly. In the busy galaxy clusters, this feedback is essential. Without the heating from black holes, the dense cluster gas would cool fast. It would rain down onto the central galaxy in a torrent, a downpour of new stars. That galaxy would become monstrous, but feedback prevents that. It keeps the gas hot and buoyant, allowing for slower, regulated growth. The cosmic web isn't a static sculpture, it's a living system. Its threads aren't just drawn by dark matter, they're colored and warmed and stirred by the galaxies they host. We're seeing an ecosystem where the inhabitants and their environment evolve together in a balance. the warmest parts of the universe, the most energetic, they're invisible. You can't see them with your eyes. You need a different vision. You need to look for X-rays. Those are the highest energy photons. They come from matter heated to millions of degrees. The gas itself, the gas in the cosmic web, it glows in that light, but to catch it, you need a special eye up in the sky. That was eROSITA, the eROSITA X-ray telescope. Its name, it stands for the Extended Röntgen Survey with an imaging telescope array. Its mission was ambitious, to do the deepest all-sky survey ever. In the soft X-ray band, to scan the entire sky, not in visible light, but in the glow of extreme heat. For years, eROSITA just mapped from a stable point in space. What it made is a revolution in how we see structure. This map isn't of stars, it isn't of galaxies. It's a map of heat, of energy. It catalogued hundreds of thousands of objects. Most are active galactic nuclei, the blazing hearts of galaxies from supermassive black holes, and it found galaxy clusters, not by their starlight. By the halos, the colossal halos of gas at multimillion degrees that surround them. Those X-ray halos, they're the true signature of a cluster's gravity well. They trace the densest nodes of the cosmic web with this clarity, but eROSITA's biggest contribution might be subtler. It's giving the first strong statistical evidence. For the X-ray glow from the filaments themselves, the rivers of warm hot gas flowing between clusters, they're incredibly hot too, just slightly less so. Their signal is incredibly faint, spread over huge areas. It's like trying to see heat haze from a single, distant road on a cold day. You can't see one filament alone. But you stack the data, you combine the signals from thousands of predicted filament locations across the sky, and a pattern emerges, a faint, diffuse X-ray glow. It aligns perfectly with the web's predicted architecture. This is a direct detection of the web's hot gas content. It's a new way to weigh the material in the strands. To measure its temperature, its distribution, this survey paints a hot picture, an energetic picture of large-scale structure. It complements the optical maps from surveys like Sloan, which show the stellar cities, and it complements the dark matter maps from gravitational lensing, which show the invisible skeleton. eROSITA shows the fiery circulatory system. That connects it all. It reveals a universe not just structured by gravity, but illuminated by the searing breath of its own most violent processes. We're seeing the cosmic web in three ways now. The dark matter through lensing, the galaxies through optical light, and the hot plasma through X-rays. Each wavelength confirms the other, building a multi-messenger understanding. Of the grand design, the web isn't a theoretical sketch anymore. It's a physical, measurable entity with mass and light and heat. The universe's architecture might have prepared a place for us. The cosmic web, that huge structure, it doesn't just arrange galaxies. It might also have a quiet say in where life can get started. It's not a direct link, but it's deep. The web's shape decides where galaxies go, and that decides where the planets are, and the neighborhood around a galaxy can matter just as much for life as the space around a star. Think about the busy hearts of big galaxy clusters. They're like the universe's major cities. Galaxies are crowded in there, so they bump into each other a lot. They merge, they get pulled apart. The space between them is filled with harsh light from all the stars and the active black holes. For any planet in a place like that, staying stable for a long time would be incredibly hard. Those slow, delicate processes that take billions of years for complex life to appear and change, they could get thrown off easily. Then there are the quieter parts. The edges of the filaments, or smaller, more separate groups like our local group. Here, the cosmic traffic is much lighter. Galaxies interacting is a rare thing. It happens over enormous stretches of time. The light and radiation there is far softer. It's a place of cosmic calm. Our Milky Way is in exactly a spot like this. We're on a filament, a kind of offshoot on the border of the huge Laniakea supercluster. We're not in a dense downtown, we're in a peaceful galactic suburb. That placement might have been key. It gave our solar system a steady, quiet corner of space for more than 4.5 billion years. Enough time for planetary chemistry to turn into biology, and for that biology to become more complex. So the cosmic web might make Goldilocks zones, but on the scale of galaxies. Not zones about temperature around a star, but zones about stability and quiet inside the universe's large-scale structure. The web's design could be quietly selecting for the conditions that allow for long, unbroken stretches of cosmic history, the kind of stretches where observers can finally look up and start to map out the very web that held them. Our address in this huge network might be more than just where we are. It could be a necessary condition for the story we're now here to tell. The maps we have now, they're revolutionary, but they're still a first draft. And the next chapter, that's being written by a new generation of instruments. Their goal is clear, to turn the cosmic web into a precision tool. The one leading this is the Dark Energy Spectroscopic Instrument, DESI. It's mounted on a telescope in Arizona. DESI isn't taking pictures, it's a spectral powerhouse. It captures light from tens of millions of galaxies and quasars, splits each one into its rainbow of colors, measures redshift with incredible accuracy. The result will be a three-dimensional map of the universe, deeper, wider, more detailed than anything before, a cosmic census on an unprecedented scale. This map isn't just for looking, it's for measuring. By plotting the positions of so many galaxies across such vast distances, scientists can trace the history of the universe's expansion. Extreme precision, they'll see how the web's geometry, the spacing of its filaments and voids has stretched and evolved. Over billions of years, that stretching is the fingerprint of dark energy. By comparing the web's structure at different cosmic epochs, DESI puts our models of dark energy to the test. The most rigorous test yet. Does it behave exactly as Einstein's cosmological constant predicts? Or does its strength change over time? The answer could confirm our current understanding, or point toward entirely new physics, and DESI is only the beginning. On the horizon is the Vera Rubin Observatory, its legacy survey of space and time, the LSST. This project will use the world's largest digital camera to scan the entire southern sky every few nights. For a decade, it will catalog billions of galaxies, detecting objects so faint they push the boundaries of the observable universe. This flood of data adds staggering depth to our charts. Statistical power. We move from seeing the major highways to mapping every back road, every country lane in the cosmic landscape. Together, these endeavors transform our relationship with the web. It's no longer just a fascinating structure to observe. It's becoming a fundamental instrument for cosmology. The cosmic web's geometry, imprinted by dark matter, stretched by dark energy, is a record. A record of the forces that have shaped everything. By reading this record with greater clarity, we use the universe's largest architecture to decode its most fundamental laws. Its composition, the web, is no longer merely what we study. It's becoming the lens through which we see everything else. A map is a snapshot. It shows what's there, but not how it got that way. To understand the forces that shape the cosmic web, you have to do more than look. You have to experiment. And since we can't rewind the universe, we build new ones. Inside machines, these are numerical simulations. They're not animations. They're not artistic renderings. They're mathematical universes, built from equations and run on supercomputers. They're like cosmic laboratories. You start with a virtual box of space, maybe 1 billion light years across. You fill it with particles, billions of them. Trillions representing dark matter and gas. You program in the laws of physics, gravity, hydrodynamics, radiation. You set the initial conditions to match the ripples we see in the cosmic microwave background. Then you press start. For months, the supercomputer calculates. It tracks the gravitational pull between every particle. It simulates gas flowing, cooling, collapsing. It models stars exploding, black holes growing. Projects like Flamingo and Astrid run these calculations. They use immense processing power to fast forward through 13.8 billion years. In weeks, the result is a digital universe. You can watch it form. First, a faint haze, then the dark matter begins to clump, drawing itself into a delicate, three-dimensional web. Filaments thicken, voids expand, gas streams along the dark matter highways. It pools at the intersections and ignites into galaxies. The simulation doesn't just show the final structure. It shows the process, the dynamic, violent dance of creation. This virtual playground lets scientists ask what-if questions, questions you can't ask in the real world. What if dark matter was slightly warmer? What if supernova were less energetic? What if black holes didn't regulate galaxy growth? You change one parameter in the code. Run the simulation again. See what kind of cosmic web emerges. By comparing these countless simulated universes to the one we actually observe, the one mapped by DESI, Rubin, and eROSITA, we can refine our theories. The simulations become a bridge. They take the torrent of raw data and filter it through our understanding of physics. They show which processes are essential. For instance, simulations proved something. Without the fierce feedback from supernova and black holes, galaxies would grow too massive too quickly. The web would look entirely different. The delicate balance we see isn't an accident. It's a signature, a constant conversation between the largest structures and the most violent events. These digital universes are more than tools. They're a new form of insight, a way to watch the story of everything play out from a God's eye view, testing our role in the narrative against all the possibilities of what might have been. The cosmic web is a story of motion. We've mapped its skeleton with dark matter, traced its rivers with hot gas, but to see it alive, you need to watch it move. That takes a different kind of vision, one that can pick up the faintest whisper of a cosmic current, which brings us to something called the kinetic Sunyaev-Zel'dovich effect. You might know the thermal version, where hot cluster gas gives a tiny boost to the ancient cosmic microwave background light. It creates a cold shadow. The kinetic effect is a close cousin, but it works differently. It's not about temperature, it senses bulk motion. Think of the cosmic microwave background as a uniform rain of photons. Falling through the universe, now picture a vast river of intergalactic gas, flowing fast along a filament of the cosmic web. As the CMB photons pass through this moving river, they scatter off the electrons inside. If the gas is flowing toward us or away from us, that collective motion leaves a minute shift, an extra Doppler effect on the scattered light. It makes an incredibly subtle hot or cold spot in the CMB map. Right at that location, detecting this signal is a monumental challenge. The temperature shift it creates is vanishingly small, often 100 times fainter than the already tiny thermal effect. It's like trying to hear a single whispered sentence in a roaring stadium. To find it, astronomers use statistical power. They take known maps of the cosmic web structure. They identify thousands of predicted filaments. Then they stack the CMB data aligned with those filaments. They combine the signals, averaging out the noise until a collective whisper of moving gas emerges from the silence. And it has emerged. In recent years, sophisticated analyzers from telescopes like the Atacama Cosmology Telescope and the Planck satellite have done it. They've detected the kinetic Sunyaev-Zel'dovich signal from the gas within the cosmic web's filaments. This is a direct detection of dynamics. It's not just a picture of the web's architecture. It's a measurement of its pulse. For the first time, we have observational proof that matter is actively streaming along these cosmic highways. We can measure, however faintly, the velocity of these vast, slow-motion rivers. The implications are profound. This confirmation moves the cosmic web from a static blueprint to a dynamic delivery system. Caught in the act, it provides direct evidence that the web is not a relic. It's a living, functioning network, continuously channeling raw material from the voids toward the hungry clusters and galaxies at its intersections. The kinetic effect lets us quantify this flow, to understand how efficiently the web redistributes the universe's baryonic matter. It turns the web's filaments from theoretical pathways into measured conduits, revealing the active role this grand design plays in the ongoing story of galaxy birth and evolution. A galaxy's spin might come from the web. The Milky Way turns slowly, its arms tracing out that spiral. Where does that motion start? It seems to start outside the galaxy, in the larger structure around it. When a galaxy is young, it pulls in gas. That gas doesn't fall straight in. It comes in along the filaments of the web like water going down a drain, and that flowing material has a slight twist to it, a tidal torque from the gravity of the web itself. That torque gives the galaxy its initial spin, its angular momentum, so the galaxy is born already turning, set in motion by these large-scale currents. This isn't just an idea. Astronomers are looking for the evidence. They map galaxies and the filaments they're in. They look for a link between a galaxy's spin and the orientation of the nearest filament. And they find a signal, a statistical tendency. Galaxies often show a preference. Their spins tend to align in certain ways with their home filament. Some spin along the length of the thread. Others might rotate with their axes perpendicular to it. The alignment is faint, just a whisper in the data. But it's there. It suggests the web shapes more than just a galaxy's location and growth. It shapes the choreography of its internal dance. The connection is profound. It links the largest scales, the billion light-year scaffolding, to an intrinsic property of a single galaxy. The direction your spiral arms point, the axis your stars orbit around, might hold an ancient memory. A memory of which cosmic highway your building blocks came down, how they flowed into the gathering cloud that became your home. This adds a layer to cosmic connectivity. We're not just placed by the web, we are set spinning by it. Our motion, our fundamental orientation in space, could be a lasting signature, a signature of our birth within a specific thread of the universe's design. The quietest sound in the universe is a radio signal. It comes from hydrogen, a proton and an electron. When the electron flips, it gives off a specific radio wave. 21 centimeters long, that's the most common note there is. We've heard it for years, but only from inside galaxies. The real story is in the space between them. In the filaments of the cosmic web, there should be huge amounts of this neutral hydrogen. It's cooler, denser than the hot plasma, more like the web's actual structure. The problem is the signal is so weak. It's a whisper lost in static, in our own radio noise, in the emptiness. To hear it, you need a new kind of ear. An ear of a different scale. That ear is being built now, the square kilometer array, the SCAR. It's not a single telescope, it's a network, thousands of radio antennas placed in deserts in South Africa and Australia. All working as one instrument. The name comes from the total area, 1 square kilometer of receivers listening. This is the next step in seeing the web. Optical telescopes see the bright knots. X-ray telescopes see the hot gas. The SKA is meant to hear the cold, the neutral hydrogen moving through the web's rivers. Its job is to map that 21-centimeter emission across huge volumes of space, to make a three-dimensional chart of the cosmic web, drawn in radio light from its most basic material. That changes things. For the first time, we won't be guessing the web from galaxies or hot gas. We'll be seeing the web itself in what it's made of. We'll trace filaments even where they're too faint for bright galaxies. we'll see the full length of each thread, from where it leaves a void to where it enters a cluster. We'll get a full count: how much hydrogen is in the web, how is it spread out from the busy intersections to the thin, empty stretches. The SKA and its earlier versions, like Meerkat and the ASCAP array, are already testing this. They're doing deep surveys, looking at patches of sky for hundreds of hours, combining signals to pull that faint hydrogen whisper from the noise. The early signs are good hints of extended hydrogen structures, lining up with the predicted web. When the full SKA is running, it will scan huge sections of the universe, building a moving map of cosmic hydrogen over time. It will show us the web's plumbing in its simplest form, show how well it moves raw material, and maybe find new features, bridges between filaments, or vast, faint pools in the deepest voids we never knew were there. That's the promise of a new window, to hear the universe's largest structure sing in its own quiet, fundamental voice. The emptiest places in the universe aren't silent. They're the great halls of the web, the empty chambers. A cosmic void isn't just a hole, it's an active part of the design. It's evolving. These voids have very few bright galaxies. But they're far from nothing. They're filled with an extremely diffuse gas, and they're threaded with the same dark matter that weaves the whole web. Just in much lower concentrations, that subtle content makes them dynamic. Because there's so little matter inside, their gravitational pull is weak. So they can expand faster than the universe's average rate. While the cosmic web tightens its knots, the voids grow more quickly. They stretch the fabric of space within them. Their boundaries are where the action happens. That's the wall where the low-density interior meets the dense filaments. Matter is slowly accreted there, relentlessly, drawn by gravity from the void onto the surrounding highways. It's like a vast, spherical room that's slowly getting larger. Its walls feed material outward into the bustling corridors that encircle it. That makes the void's edge a site of continuous construction, subtle construction. Some cosmologists also suspect these underdense regions might be where dark energy leaves a slightly stronger imprint. Dark energy, the force accelerating cosmic expansion. With so little gravity to fight against, the repulsive push of dark energy could be a fraction more detectable. In the deep quiet of a void, that turns these cosmic deserts into exceptional natural laboratories. Studying voids gives us a clean test for our models. Models of gravity and cosmic evolution. In the dense knots of the web, the physics is incredibly complex. Galaxies collide, black holes erupt, gas churns. But inside a void, the environment is simple, it's quiet. The rules play out in a slow, minimalist fashion, free from the violent chaos of the clusters. By observing how voids expand, how their few isolated galaxies behave, how their shapes evolve, we can see the pure effects, the effects of cosmology's fundamental forces at work. The void and the filament are two sides of the same coin, sculpted by the same gravitational hands. One is defined by presence, the other by absence. You can't truly understand the glittering structure of the cosmic web without understanding the profound emptiness that gives it form, the growing emptiness. They are the positive and negative spaces in the universe's self-portrait. Each gives meaning to the other. That oldest light, the cosmic microwave background. It's more than a snapshot, it's a record of its trip, 13.8 billion years of travel, and the universe it's moving through hasn't been still. It's been changing shape. That change leaves a mark, a subtle one, the integrated Sachs-Wolfe effect. Think about one photon from that background light. Starting its journey to us, it's not moving through empty, flat space. It's moving through the gravity of the cosmic web, the hills and valleys. Picture rolling a marble up a hill. That takes energy, so when the photon enters a massive region, a cluster or a filament, it has to climb out of that gravitational well. That costs it energy. It stretches the wavelength, makes it a little cooler, a redshift, then when it leaves it rolls downhill. It gains that energy back, a blue shift, it gets warmer. In a static universe where those hills and valleys don't change, the energy lost on the way in is regained on the way out. They cancel. The photon arrives as it started. Unchanged, but our universe isn't static, it's evolving. Dark energy is causing it to expand faster and faster. This acceleration does something to the gravitational landscape. It makes the hills flatten, the valleys become shallower. Over time, the gravitational potentials are decaying, so our photon enters a cluster. It climbs a hill. But by the time it leaves, that hill is a little lower. The photon doesn't get back all the energy it spent. There's a tiny net loss. That photon arrives at our telescopes slightly cooler than it should. And the opposite happens for a photon passing through a large, growing void, a gravitational valley. The valley becomes shallower as it expands, so the photon gains a tiny net energy. It arrives slightly warmer. The result is a faint pattern, hot and cold spots on the CMB, directly linked to the positions of the large-scale structure. Hot spots over voids, cold spots over clusters and filaments. Finding this signal is a huge challenge. The temperature shifts are tiny, millionths of a degree. To find it, scientists take maps of the cosmic web from galaxy surveys. They cross-correlate them with the precise maps of the CMB from missions like Planck. They look for a statistical link. Do the cold spots in the CMB line up, on average, with massive galaxy clusters? Do the warm spots sit over cosmic voids? After years of analysis, the answer is yes. The correlation is there. That's the integrated Sachs-Wolfe effect. Its detection is a triumph, but its meaning goes deeper. It's independent evidence for dark energy. Only in an accelerating universe do gravitational potentials decay this way, leaving this fingerprint on the ancient light. And it does more. It forges a direct link between the universe's infancy and its maturity. The CMB shows us the seeds, the galaxy surveys show us the grown forest. The ISW effect shows us the growth itself. It lets us witness, in the faintest temperature ripples, the dynamic evolution of the cosmic web across all of cosmic time. It's the universe's own time-lapse written in the light of its birth. The story of the web has always been told in light, the glow of galaxies, the heat of X-ray gas. The cold imprints on ancient radiation, but light is just one language. The universe speaks in others, in particles, in waves. It carries different secrets. And now we're entering an era, the multi-messenger universe, where to understand the cosmic web, you have to listen in every way possible. One of these messengers arrives not as a wave, but as a bullet. A cosmic ray. These aren't rays of light, they're atomic nuclei, protons, the hearts of atoms, accelerated almost to the speed of light. They come from outside our galaxy, from the most violent events out there. And when they finally hit our atmosphere, they create a shower of secondary particles we can detect, but their journey here is a mystery. They travel for millions of years. And on that journey, they have to pass through the cosmic web. Scientists think the filaments of the web are threaded with magnetic fields, incredibly faint fields, but stretched across those vast distances. And as these charged cosmic ray bullets fly, those magnetic fields bend their paths, they twist them, they turn them, they scramble any clear sense of where the rays came from. That's been a major frustration, trying to trace cosmic rays back to their sources. But that scrambling itself is a clue. It's a record. The specific pattern of deflections, if we could decode it, could tell us about the strength of those fields. The structure of the magnetic fields woven through the web's architecture. So by mapping the arrival directions of countless cosmic rays, by untangling the statistical patterns, we might one day not see the web in light, but feel its magnetic texture. Feel it through the bent paths of these high-energy travelers. Then there's the most elusive messenger, the ripple in spacetime itself, a gravitational wave. We've learned to detect the loud, crashing waves from merging black holes and neutron stars, but beneath those events, theorists say there should be a background hum. A faint, diffuse sea of gravitational waves from the very early universe, from processes in the first fractions of a second. This primordial hum would have been generated when the universe's large-scale structure, the seeds of the web, was first being set. Detecting that signal is a monumental challenge far beyond our current technology. It would require an observatory in space, exquisitely quiet, measuring the subtle stretching of spacetime across the entire cosmos. But if we could ever hear that hum, it would be a direct recording, a recording of the universe's birth pangs. It would tell us about the forces that imprinted the first overdensities. The very blueprint from which the dark matter skeleton and later the luminous web would grow. It would be the soundtrack to the web's creation. The principle here is profound. The cosmic web is a distribution of mass and energy, so any cosmic messenger that carries information about mass and energy could, in theory, be used to chart its form. We've mapped it with photons. We may one day trace its magnetic fields with particles, and we might ultimately listen to the echo of its birth, the faintest tremors of spacetime. Each new messenger doesn't replace the old. It layers a new sense onto our understanding, sight, touch, and sound for the cosmos. Together, they promise a deeper portrait. A richer portrait of the grand design, revealing dimensions of its story that light alone could never tell. The universe expands, and that expansion leaves an echo in how everything is arranged. A frozen ripple from when everything was just this hot, liquid fire. In the first few 100,000 years, the universe was a dense plasma, a soup of particles and light. And in that soup, sound waves moved through, pressure waves from gravity pulling matter together and radiation pushing it apart, real acoustic oscillations rippling through the whole cosmos. Then the universe cooled, the fog cleared, light and matter separated, and those sound waves just froze in place. Their imprint was left as a subtle pattern in where matter ended up. A slight tendency for galaxies to be a specific distance apart. That distance became a standard ruler, a cosmic yardstick etched into everything. That's the Baryon acoustic oscillation. A fossilized sound wave from the very beginning. To find it, you have to measure the universe's structure with incredible precision. That was the task for BOSS and later eBOSS. These weren't separate telescopes, they were programs within the Sloan Digital Sky Survey. Their instruments were built for one thing, to capture the spectra of millions of the most distant objects. Galaxies, quasars, the faint lines of the Lyman-Alpha forest. They mapped the 3D positions of these tracers in unprecedented detail, making the most precise charts of the cosmic web across huge stretches of time. But they weren't just mapping to make a picture, they were measuring, searching for that subtle, repeating signal in how matter clusters, that preferred separation. The echo of an ancient sound, the method is statistical. You take a map of, say, 1,000,000 galaxies. You calculate the probability that any two galaxies are a given distance apart. In a random distribution, that probability would be smooth. But because of the cosmic web, galaxies are more likely to be at certain distances. They cluster along filaments and walls. And on top of that web-like clustering, there's a tiny bump, a slight excess of galaxy pairs separated by about 500 million light-years. That specific distance is the Baryons scale. The radius of that frozen sound wave, stretched by the expansion of the universe over billions of years. BOSS and eBOSS didn't measure this scale just once. They measured it at different cosmic epochs. By looking at nearer galaxies, they measured the ruler more recently. By looking at distant quasars and the Lyman-Alpha forest, they measured it when the universe was much younger. This gave them a series of snapshots. They could see how the length of that standard ruler appeared to change over time, but the ruler itself isn't changing. The physics of that early sound wave set its true size. What changes is how we see it, because the space it's in is stretching. The apparent size of the ruler tells us how much the universe has expanded between when the imprint was made and when we observe it. So by measuring the apparent BAO scale at different times, these surveys directly charted the expansion history of the universe. They turned the cosmic web, that grand, spongy structure of galaxies and gas, into a calibrated instrument. The web's geometry became the dial on a cosmic speedometer. The results confirmed our cosmological model. They gave some of the cleanest evidence for dark energy and its accelerating effect. They showed the expansion history traced by these frozen sound waves matched predictions from the cosmic microwave background, two completely independent probes. One from the universe's infancy, one from its adolescence and maturity, telling the same story. That's maybe the deepest legacy of understanding the cosmic web. It's not just a structure we live in, it's a tool we can use. Its pattern, the distribution of galaxies that seems so complex, holds a simple, pristine signal from the first moments. A whisper from the hot beginning, carried on the architecture of the present. By learning to read the web's intricate design, we found a way to measure time and to weigh the invisible forces shaping our ultimate fate. The universe isn't just scattered points, it's one thing, a single tapestry. And when you look at the cosmic web, you see this order, this breathtaking order, where dark matter, these invisible threads, they orchestrate everything. They orchestrate the whole ballet of galaxies, and that's not a metaphor. It's the actual architecture, the fundamental architecture of reality. From those first quantum seeds, imprinted in the Big Bang's afterglow, all the way to the filaments and voids we map now with our telescopes. That web is the hidden framework. It's the sculptor. It channels gas, rivers of gas, to birth stars. It's the architect. It gathers galaxies into clusters right at the intersections. And it might be the choreographer, too, setting galaxies spinning, their motion a kind of memory, a lasting memory of the cosmic currents that formed them. For a long time, we only saw the bright knots, the bright spots in the tapestry. Now we're learning to see the threads. We trace them with bent light, with a faint X-ray glow of million-degree plasma, with a statistical whisper of hydrogen in the radio silence. And each new observation, from the James Webb Space Telescope looking back in deep time to the huge galaxy surveys like DESI, they move us. They move us from just observing the structure to using it as a precision instrument. The geometry of the cosmic web, stretched and shaped over eons, has become our most powerful tool. For measuring the invisible forces, for weighing dark matter, for testing dark energy, for reading the universe's expansion history like a clock, that understanding changes our place in the story. We're not passive spectators, not in a random, empty arena. We're participants, woven into the design. Our galaxy spins on a quiet suburban lane of this vast network. And that placement, that might be what granted the stability needed for our own story to unfold. The cosmic web teaches that isolation is an illusion. We are connected by gravity, by flowing matter, to every cluster and every void. We're part of something vastly larger, more intricate than we imagined. A beautifully organized cosmos, secretly structured, waiting to be fully understood. The darkness between the stars isn't empty, it's full of design. And we're just starting to learn its language.